Good morning guys, I hope you're all doing okay. Welcome to today's worked exam answer video where I'm having a look at a paper 2 organic synthesis question whereby we've got 3 reaction steps. We don't know what any of those 3 reactions are. We know we're starting with butene and we know we are making, by the end of reaction 3, an N-substituted amide. We have the structural formula of butene, we've then got the molecular formulae for the remaining 2 intermediates and 1 product. And for each of these 3 reactions, we have to state a reagent, give the structure of the product, and name the mechanism of the reaction. Detailed mechanisms are not required, so we don't need to draw them out, we don't need to give any equations, we don't need to give conditions, or types of reactions. So for 9 marks, we've got 3 reactions and we've got 3 things that we need to do for each. So it's quite nice in that we can see fairly easily here where the marks are going to come from. So this is going to rely on us knowing what we can do with an alkene in terms of what we can turn that into, and then what can we do with the product of that, and then what can we do with the product of that. And it helps that we have the molecular formula because we can see what's changed between the start point of reaction 1 and the end of reaction 1, start point of reaction 2, end of reaction 2, and so on. Now it might be you don't get given molecular formulae here. You might get told that this is X and this is Y. And so that would be a harder question, of course, because you don't have anything to help you to see, oh, what could I turn it into that contains a Br or an N, for example. But hopefully by Tuesday you will have, not Tuesday, sorry, it's Monday, isn't it? Hopefully by Monday you will have all of these sort of steps and conditions and mechanisms committed to memory. So let's dive in. Starting with butene, so we're starting with an alkene. What we can see in the product of reaction 1 is that we've got a Br. We can also see that the number of hydrogens is now 9, so in total we've got sort of 10 things attached to the 4 carbons, which matches the general formula for an alkane, sort of CnH2n plus 2. So that would suggest the double bond is being broken, and we're going to need to have one of the carbons gaining a hydrogen and one of the carbons gaining a bromine. So that should hopefully be sufficient for you to figure out that reaction 1 is going to be electrophilic addition. And in terms of how I can spot that, if I couldn't kind of recall in the exam that this was electrophilic addition, and what could I do? Again, look at what atoms we had before and after, and what you could do, if it helps, is to write out a molecular formula for the butene, so C4H8. So no atoms of the C4H8 have left, we've just added a hydrogen and a bromine, so addition. And because we have a double bond, which is a region of high electron density, we're not going to be able to use a nucleophile, because a nucleophile's lone pair is not going to be attracted to negatively charged electrons in the carbon-carbon double bond. So it can't be a nucleophilic reaction, so electrophilic instead. The double bond can use the electrons to attack one of the atoms in the electrophile. So the reagent we're going to have to give here is going to be the electrophile. So if we've added a H and a bromine, it's going to be HBr. And then we have to give the structure of the product. Now it doesn't say what type of structure, so you could do it skeletally, you could do it probably in structural formula, sort of like they've done for the butene, or you could draw it out. I'm a big fan of having things drawn out because I'm very visual and that helps, but it would be your choice. Obviously, if a question specified how it wanted you to draw the structure, then make sure you do as it's asking, but here it wouldn't matter. Now it also wouldn't matter here which of the two carbons in the original butene gets the hydrogen and which gets the Br, because either way round we're going to get the exact same product. So that would be something you would need to think about in some electrophilic addition reactions, but here we don't. So I'm going to put it there, and we've made 2-bromobutane. Okay, so that's 3 marks already in the bag. Next up, we've got reaction 2. So we start now with our 2-bromobutane, and we can see, again, if we look at what's changed, that we had the bromine of the halogenoalkane, but it's now a nitrogen. And we also had 9 hydrogens before, and we've now got 11. So we've got not addition this time, because the bromine is no longer there in the product of reaction 2, so it can't be addition. So it could either be substitution or some sort of addition elimination, but we only ever do addition elimination when we're starting with an acyl chloride, of which this is not one. So that would suggest it's going to be substitution. And because this no longer has the double bond, it's not going to be an electrophilic substitution, because it doesn't have a region of high electron density. And the carbon-bromine bond, because the carbon will be delta positive, bromine delta negative due to the difference in electronegativity, nucleophile can attack the carbon. So that would suggest that reaction 2 is nucleophilic substitution. And in order for there to be a nitrogen and 2 extra hydrogens, we're going to need to use ammonia. Now, it doesn't ask for conditions here, but what we do need to remember is that if we're trying to make the primary amine and not get further or successive nucleophilic substitution reactions, we would want to use an excess of ammonia, because that then kind of outcompetes the primary amine, which can also act as a nucleophile, and stops that from attacking the remaining halogenoalkane, just based on the laws of probability. Now, you wouldn't need the excess here because it hasn't asked for a condition, but again, on a wider scale, I thought it'd be useful for me to mention that and put that in. And then the structure of our product now, we just need to swap where the bromine was for an NH2. And again, it doesn't matter how we draw out the structure. I'm going for full displayed, but a mix of displayed and structural or skeletal would be fine. Okay, now the nice thing here is they've told us again, like they did at the start point, what we're working towards. Now, we don't know exactly what N-substituted amide it is, but we know it's an N-substituted amide, and we've got its molecular formula. So we can see that we've gone from 4 carbons in our amine to 6 carbons in our N-substituted amide. We've also gone up 2 hydrogens, so we're now on 13 of those, and we've got the oxygen. Now, the amine is going to act as the nucleophile, so when we're thinking about the reagent we're going to add, we need to think about what is going to bring those 2 extra carbons, 2 extra electrons, 2 extra hydrogens, and the oxygen. I don't know what my brain was doing then, I'm very sorry. Now, when we've got N-substituted amides, one of the things that might help in terms of the recall memory side of things is that we can only make an N-substituted amide in nucleophilic addition elimination. So that is a helpful kind of thing to have stored away in the brain. And I'm going to stop talking and writing at the same time. My brain doesn't seem to be able to handle that today. So nucleophilic addition elimination. And when we do nucleophilic addition elimination, the start point is an acyl chloride. So based on what we have in the amine and what we need to get for our N-substituted amide, the acyl chloride is going to have 2 carbons. So one of those carbons will have to be for the functional group. So it's going to be CH3COCl. So that's going to bring the oxygen, it's going to bring the 2 extra carbons, and then it's bringing 3 hydrogens. We only need 2, but of course one of the hydrogens from the amine group will have to leave in the elimination step. Now, some people may find it tricky to draw the product without doing the mechanism, and if that's the case, there's nothing to stop you from drawing the mechanism, obviously. If that helps and it's going to get you the right structure for the product, do it. If you can do it without drawing the mechanism, that would be perhaps more time efficient, and also you wouldn't be kind of writing things down that you're not getting any marks for. But if you need to do it, do it. Now, in terms of what's happening, the nitrogen's lone pair is going to attack the carbon of the C double bond O. And in the first step, we're adding, so the nucleophile will add on, the C double bond O will break to form a C single bond O, and the CH3 and the Cl will still be bonded at that point as well. That would then be our intermediate that we would draw, and then in the second step, the elimination part, we're going to reform the CO double bond, we're going to eliminate the chlorine and the nitrogen, which will now be forming 4 bonds, loses one of its hydrogens to replenish its lone pair, and that would be our 3 curly arrows in the elimination step. So if you know and can visualize the mechanism, then you can possibly draw out the structure without needing to draw the whole mechanism. So the first part is going to be the CH3C double bond O from the acyl chloride. And then comes the nitrogen that attacked that carbon because it was the nucleophile. It's going to have 1 hydrogen on it, and this is why it's an N-substituted amide, because the other bond that the nitrogen forms isn't to a hydrogen, it's to this carbon here. So we've then got that carbon, which has 2 bonds to carbon. So one will be a methyl group and the other will be the sort of longest chain, if you will. So 3 and then 1 up there. And that again is why this question is a little bit perhaps harder. The NH2 group, our amine group, was not on the end of the chain. It was on one of the middle carbons, and therefore we get a kinked chain for our alkyl group bonded to the nitrogen. So if we were asked to name that, which I really don't think you would be, but when we're naming any N-substituted amide, we do N dash, name the alkyl group, that's attached to the nitrogen, and then we'd name the rest of it like we would a normal amide, so ethan amide or ethanamide. Here we would probably have to go with 1 methyl, so N dash 1 methyl propyl ethanamide. So let's hope they don't ask anything like that. If we got rid of the methyl, we'd go with N-propyl ethanamide, which is possibly something they may do. Have I gone through everything? Nice to check. I've got a reagent for each, I've got the structure of the product for each, and I've got the name of the mechanism for each. 9 marks. If you know it, brilliant. If you're good with your organic reactions, brilliant. If you're not, all you can do over the next few days is try and learn what you can, learn the connections, learn what we can turn an alkene into, learn what we can turn a halogen or alkane into, etc. Practice drawing out the mechanisms as much as you can, blurt out all the reagents and conditions and names of mechanisms, names of processes, etc. If there's anything else I can do to help, as always, please let me know. I wish you all the very best with the rest of your revision. Take care, everyone, and I'll catch you soon. Bye.